pleasure to introduce Nikita Kalinin. He's at the moment at the CINVESTAV, and he will talk about a new formula for P.
Yeah, thank you very much for the possibility to speak here on this nice conference. I really like Mexico City so far. Okay, I will be talking city. Okay, you see that's the new formula, and this talk will be kind of entertaining. So don't expect big science here or like complicated proof. It will be kind of story how we found this formula, how we discovered it. So here you see a sum by all pairs of integer vectors. Some chalk. So we can see the all pairs of integer vectors in the first quadrant, such that the area of parallelogram is 1. And we take this triangle, and it has 3 sides, like this one, x, y, and z. And here in parentheses we have this triangle inequality defect. We have sum of lengths of 2 sides minus sum of diagonal in this parallelogram. And then it happens that if you sum up all squares of such stuff, you got P. Okay, so and how we discovered such a formula? Oh, not how we discovered it. So that's the story. So I think that mathematics should be social and kind of accessible to people. And what is the best way to popularize such a formula? It's definitely not to publish it. Because okay, if you publish it, like 2 people read it, and okay, that's it. So I go to Math-Overflow, and kind of I say that we have a proof, but we don't want to tell you the proof. Try to prove it by yourself, because it's a nice formula. Probably there should be some nice proof. And also I expect the same of you, because you are a specialist in group theory, know this category stuff. Probably there should be some scientific proof, because we have a really proof for school. Like
wait. Your proof was for any n?
No. My proof is only for n equals 2. So we know how to prove this formula. Mm-hmm. And so we don't know, okay, we know that if you put here 1, we have 2 here. But I will explain some, okay, why is that? And also it's proven. And it's open question, what happens if here you have n? I calculated on my laptop, I have some numbers. Then I found some site where you can put a number, and this site produces your formula for this number. So for 2, it produces 2. For 2 minus p over 2, it produces 2 minus p over 2. But for other numbers, it produces something strange, like 1 plus phi as number of failure divided by something square. Okay, it's totally crazy stuff, and it's not true, definitely. So, okay. So we go to Math-Overflow and ask, and 2 guys proved it in also very elementary way, without anything. And you see, it has like 71 votes. It's quite big, quite large number. And for example, this question is among the following questions. So that's the questions with 71 votes. About jokes, about how to be a successful mathematician. Sure, like, is Euclid dead? Yeah, how can I see LaTeX in email? It's also very important. And the last one is period and commas in mathematical writing. So this kind of our questions here, it's very good. So it's really important for society. Okay, so that's now I begin the story how we discovered such a formula. With Misha Shkolnikov, we were doing some sampiles, and I'll give you some definitions. So you have some graph, for example, a subset of the standard lattice of Z2, And you have a function which basically counts the number of grains at every point. Sometimes it's called grains, cheese, or something. So you have something inverse graph, and if you have more than 4 grains, you say that the vertex is unstable and you can topple it. And the toppling goes like that. So we have 4, and it's kind of communist distribution of goods. So if somebody has 4, then its neighbors take 1. To kind of
Leave you with 0.
yeah, but also you see neighbors and neighbors also became 4, and their neighbors take something. So it's kind of, it's more or less, it spreads, the good spreads across society. Goods cannot concentrate in one place. And then you continue until the process finishes. It's clear that the process is always finished because, for example, if we have a toppling here, then 1 grain goes abroad, and so the system loses this grain which goes abroad. So this process always terminates, and this model was discovered as a mathematical model for power laws. Probably you know something about power laws in natural sciences. For example, the earthquakes. There are, like, if you take some area and then you measure how many earthquakes of given magnitude happens, then, for example, in average, 1 earthquake of magnitude 7, 10 of magnitude 6, 100 of magnitude 5, and so on. And the same law is everywhere, like for prices in stock market, for car traffic, for everything. And some guys tried to invent some mathematical model which also shows such a behavior, and so they invented sand piles. But clearly such an easy model, simple model, was defined before. For example, number theory. When you have a curve which degenerates to components and you want to keep track of some divisors, you have basically the same rules. So it's kind of distribution of zeros of okay. I cannot explain it. Okay, now I explain how tropical curves appear in sand piles. So we start with the maximal stable state. So a state which has 3 everywhere, like everybody is the most happy it's possible. And then you can see the some convex domain in R2, and you take a very thin grid with step 1/n, where n is big. And as my model, I consider the graph inside this omega. And I put 3 grains at every vertex, and also I have chosen some points. You see the blue points. And at that point, I add 1 more grain. And so the initial state here, it's like 3 everywhere, and 4 here, 4 here, and 4 here. So I need to round my points. And it's unstable, so I need to relax it. And it was Cartel and company who ran some experiments, and they found beautiful pictures. I will show the beautiful pictures. In particular, after the relaxation, you again have almost 3 everywhere. So you start with 3 everywhere, and for some points you relax, and again you have almost maximal stable state. But Cartel and company, they were, how it's called, applied mathematicians doing physics. So they studied some physics model by computer experiments. So they didn't care about proofs at all. So they discovered beautiful pictures. They said, okay, it's nice pictures. They obey such laws and so on, but they didn't try to prove it. And with my collaborator, with Misha, we proved it. Okay, that's the beautiful pictures. So, for example, if my omega is a circle, then I put only 1 grain in the center, 1 additional grain to the center. And here you see what happens after the relaxation. So it's when you rescale the picture, when you rescale this mesh of the grid, it stabilizes. It stabilizes to a tropical curve. If you want a tropical curve, just piecewise linear graph in my domain. And we will see these pictures after that. explain some idea about proof. So what does it mean if we start with 3 grains everywhere and we end up with 3 grains everywhere? I claim that if I count the number of topplings at every point, I know that it's function h. Then this property that the number of grains is the same before relaxation and after relaxation is equivalent to such an identity. So in all lectures about St. Piles, I ask people to prove it. If you see it like third time or fourth time, you shouldn't prove it. But if you see it the first time, try to prove it now. Probably we'll have some questions about the model, so prove it. It's easy. Возьмем по Володе.
You're sure about the 4? I mean, yes?
Sorry?
There is this coefficient of 4.
Yes, sure.
Because it's 4 adjacent squares.
Yeah. Remember that each vertex has 4 neighbors.
Every time you earn 1 when it's 1 of
Every
each
problem
four.
you lose 4.
But,
Yes.
but then you lose 4. So I mean,
It's indeed a conservation law.
Yeah. Okay, so we count the number of incoming and outgoing grains, right? So if we start with 3 and we end up with 3, then the number of incoming equals the number of outgoing. When a neighbor of x, y topples, it sends 1 grain to our point xy. And that's exactly the number of toppling in all 4 neighbors. Right? That's the number of grains which came to my vertex. And each time I have a toppling at my vertex, I lose 4. So that's why here -4. Okay? Okay, so, and that means that if kind of empirically I know that I started with 3 everywhere and I end up with 3 everywhere, it means that my function of topplings should be a kind of harmonic, right? Because that's exactly the definition of discrete Laplacian. And so, which harmonic functions you know? I know linear functions, basically. And linear functions are especially good because what we know that our function is integer variant. And also one can prove that St. Piles are kind of lazy. They try to do as minimal number of topplings as possible. So we are looking for harmonic minimal function. And so it's linear. There are no harmonic functions defined on big domains of lattice, which are not which are less than linear. So you can prove it's unions. So if you have a big domain, how you estimate by linear function of your harmonic positive function, then it is indeed itself it is linear. Okay, so it's kind of very natural guess that our function of toppling should be piecewise linear. And then okay, we understand that at the locus where the function is harmonic, we end up with 3. So not 3. It's exactly where the function is not harmonic. If you imagine a piecewise linear function, what is the set where it's not harmonic? It is exactly its set of non-smoothness. It's corner locus. So now you can understand easily why we have such pictures. So you should imagine here kind of piecewise linear function, and that's exactly the corner locus of my piecewise linear function. Okay? So that's the main guy in our story. So this piecewise linear function. We discovered it. And okay, that's it. Somehow it's not visible, but okay, that's piecewise linear function, and that's its corner locus. Now I will explain what is this piecewise linear function and what is the relation to P. Okay, for P it's now clear. P is the area of a disk. And so now we want to use this piecewise linear function, exactly this one, and we will try to understand the area of the disk. So what is this piecewise linear function? We can define it for any convex domain. And now it's our ongoing project with Misha Shkolnikov, with Ernesto, with Juliet, and with Aldo, and I don't know, with other people. So since we know that for any convex domain there exists some kind of natural piecewise linear function, we can somehow use it for non-commutative toric geometry, for non-commutative toric variety constructed by these domains, and so on. And so here's the definition. So for each ij in lattice, we find the minimum of this function, and then define this L omega ij. What is this function? Basically, it's have this omega, and you choose the coefficient Cij such that the zero set, it's a tangent line to my omega, right? Exactly. And so my function is like that. So it's positive on omega, and kind of it's the minimal positive function with given slope. Okay. And so what can I do? I can take such functions for all ij and take the minimum. And we say that it's a tropical distance function. It's kind of measures the distance from a point inside of a domain to its boundary. Okay, function, and it is zero on the boundary, as you can prove. And for example, for the circle, it's a function like that, exactly this function. And so we proved the theorem that when you have the sand-pile model, you drop some additional sand, then you relax, you basically always have a function like that, then you modify it, and you have a tropical curve. Okay? So this function is natural and important. So now we go to the Gauss circle problem. So what to do if you have a kind of lattice respecting linear function? All our functions in this construction, they have integer slope. And so one can do this as the following. So let's consider big circle or any other figure, and we have, oh wait, I want to tell you first about Gauss circle problem, but probably everybody knows about it. You can see the circle of radius n, and then you want to know how many lattice points this disk contains. All of them. It's clear that the number of points is equal approximately to the area of the circle, right? And so it's Pn square. But also there is additional term, and the Gauss proved that this additional term is no more than of order n. And current estimates are like that. So we know that this additional term is of order at least n to the power 1/2. It is believed that it's of order n to the power 1/2 plus epsilon, plus any epsilon. But the current estimate from above that it's okay, it's this notation that's E or B. That's what I mean. Okay, and it is believed that for any epsilon bigger than 0, f of order n plus epsilon. But it's not proven, and it's very hard problem. And okay, so we're trying to use our function to approach this problem. It's a very crazy idea. because problem is very difficult, function is very stupid, but who knows? And we try to do it like in physics. So we didn't care about proofs at all, we just tried to apply it and give some identities, obtain this, prove something and so on. So we have our function f, which is this tropical distance function for the circle. And let's imagine that this function is integer valued at integer points. Okay? It's approximately like that, because your function has integer slope. Okay, this coefficient Cij, they're not quite integer, but okay, they're almost integer. So if you have a very big circle, all of them kind of integers. So how to count the latest points in the circle if you have such a function? You can count by level sets. You have the points where our function is 0, function is 1, and so on. So we can cut up all these level sets and try to understand how many points we have in level set. And that's kind of easier. So as you remember, our function is a polytope. And when you project it down, you have kind of tropical curve. So something like that. So it's a projection of our function, of the corner lobes of our function here. So what is the level set? So level set starts like that. So you have all integer points here, 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 etc. So what is the next level set? Here, here. And it's kind of more or less clear that each time we go to the next level set, we increase +1 integer point here, +1 integer point here, and so on.
Sorry, the function e is the indicator function?
No. The function e is minimal of all these linear functions.
That was not the h function?
Yeah, right. H was the function of top links, and the function E is this one. So
okay.
it's defined for any convex domain as a minimum of all these functions like that.
Sorry.
For example, here it is, this one.
Okay.
So basically here what we do, so for each direction we take the tangent in this direction to the circle and take the function which gives this tangent. Take the minimum.
Okay, thank you.
Okay, and so it is clear that, okay, so to calculate the number of points in each level set, we need to know the number of sides of a face here, and what happens when we have a vertex here. So first of all, we have here 1 point, we have 2 points, 3 points, 4 points, and so on. So by some heuristic arguments like that, we come to the following formula. So first of all, we need to find the vertices of our function, and then we need to sum up something by all these vertices. Okay, now is lemma. Lemma says that all the vertices in bijection with elements of SL to Z. And it's kind of understandable. So you start with a circle. Let's draw all the sides of my function one by one. So first of all, I draw tangents of direction like that. Okay, so I have function like that. It has one vertex here. Then I have two vectors, 0, 1 and 1, 0. I can take their sum and draw tangents here, and it cuts my polygon. And it adds one vertex, right? Then I take two vectors, 0, 1 and 1, 1. Take their sum at the tangent perpendicular to the direction, and again it cuts a bit of polytope and gives a new vertex. Then, by direct calculation, you can show that, okay, and then we expect such a formula. So we have a area of the disk on the right. And as I said, that if you have a vertex, then you have some kind of such a number here. So you have 1 point plus 2 plus 3 plus 4, etc. So that's why you should have some of this n choose 2 things. It's totally wrong. It was kind of heuristic arguments. That's how we discovered such a formula, and we wanted to use it to prove something about Gauss circle problem. Okay, so that's the formula that we expect, and we tried to verify it. And again, we did another wrong step. We say, okay, what is the leading term here? It's probably sum of p of p squared. So the leading term should be kind of p. It's again wrong, because the leading term here is fp, because usually fp is very, very small. When you have such a function, then all the vertices are very, 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 very down. So the leading term is the first degree, not the second. Second degree is less. But okay, nevertheless, we thought, okay, let's try to sum up the squares. And then it happens that if you plug in this in computer, you play with sum of squares, so this function of p, you got 2 minus p over 2. And sum of fp is 2, and you see the difference over 2, exactly p over 4. Okay, and this f of p is exactly the function in the beginning. This one. And so that's open question, what happens if n is bigger than 2. And there is a proof on matter flow. So you consider such functions, and then you telescope.
Plus, what is x sub index y?
Projection.
It's the length of the projection.
Oh, okay.
I want to go to the restroom for a minute. Sorry. I'll return.
Miscal was good. Now you continue.
Exactly.
So just take the difference. Phi 1 minus phi 1 minus phi 1. That's easy. And the other one is also easy. It's cancellation of terms. It's just cancellation of terms. Both are very, very good.
Where is pi here?
No. Not yet.
In the computer calculation.
No, it should just be pi somewhere, like 200.
What is the first page of the proof? The
So computer calculation means
So yes.
No, the next one is thank you.
No.
which one?
No, the other direction.
Computer calculation.
No, but there is an elementary proof. No. It's very easy.
That's the fun.
No, was it pre todos los puntos. Questions.
Questions to
Well, ahora
With thanks.
sí, pero sí.
Yeah.
Sí.
¿Qué pasó ayer? Pues mira. No nos acordamos.
Sí, las medidas.
Well, we thank the speaker. Questions?
Yeah. Sorry.
Are you okay?
Yeah. Very good.
So just the proof, just this math overflow.
Yeah, what is the telescope? What are the telescope?
Okay, you want to sum up all these identities by all the pairs of vectors x, y. And they all kind of telescope. And the only thing you need to prove that, okay, for example, in the for the first formula, when you sum up without squares, for example, yeah. Here, for example, if you take the sum without square to the power 1, then you have for each vector you have its length many times, right? And so the only thing you need is to kind of to count how many times you have it, and then to prove that indeed when you go to infinity, this series converges. So it's more a question of convergence, not a question of because it's not clear. So you have just sum, everything disappears, but okay. And the same for sum of squares here. So after you present it as such a function through this function phi2, then again when you just sum up your telescope, you need to prove some convergence stuff. That if you take all the vectors in a big circle, then all these terms which should disappear, they are small.
Yeah, so this is for the circle, and you get SL2 and a kind of more or less clear Y.
Yes.
Okay. What happens for other domains? Yes.
That's for parabola.
Wow.
It's a new formula for 2/3.
Which is more important for 1 or 124.
Yeah, it's a more important constant.
This is string theory.
Yeah, definitely. Basically, we can produce such formula for any curve. Just the terms are not so funny. I can give you the secret how to produce such formulas. For example, what you should do for parabola. So you consider again a part of parabola like 1 minus x squared here. And then you need to prove small lemma. Lemma is as follows. So if you have any curve, then you draw tangents. Tangents here, tangents here, tangents here. Okay? And so I want to know the area of such a triangle. Okay? It happens the following. So if my, okay, let's say we have a curves of ax plus by plus c, ax plus by plus c, ax plus by plus c. So now another exercise. Let's say we have such a 3 curves which are tangent to a curve, but it doesn't matter now. And let's say that a plus is just a plus a, like so, like in our ordinary situation. So we have 2 vectors and we have their sum. So what is the area of this triangle in terms of c, c prime, and c double prime? Can you guess as a physicist? So it should be quadratic in c, c prime, and c2 prime, right? Because when you move one curve, well, when you move one line, and so the area changes quadratically. What else? You know that if this third line passes through this point, the area is 0, right? So how can we combine C, this dada C to primes to get 0? But clearly that if we have such identity, then if C double prime equals C plus C prime, then all three curves pass through one point. So in that case we expect 0. Okay, so
This quadratic
Quadratic?
difference.
The difference of the squares.
right. So it's something is like that. Probably we should divide by 2 with some constant. And you have seen this quadrat of something. Because when you take the circle and when you take the direction AB, what is the equation of the tangent here? It's ax plus by minus square root of a plus b squared. Right? So that explains how, that explains our proof. That we start with a circle, then you cut out first triangle. That's exactly such a formula for lengths of vectors, for these coefficients in equations. Then you take the sum of vectors 1, 1 and 0, 1, and you cut up another triangle. And its area again is given by such a difference. And so that's explain you the first formula. We just start with such part, and then we one by one we cut out all the triangles. And so the sum of the areas of such things is exactly b. And the same you can do for any curve. Again, so we have this lemma. So what we need to do? We need to find the coefficients for tangents of given directions. And it happens that if you have a parabola like that, and when you have three tangents of directions orthogonal to AB, CD, and A plus B, C plus D, and you take, if you find the coefficients, you find this difference happens to be this one. And why do you have here 2B and 2D? Because for the circle, we start with the tangents here of direction 0, 1 and 1, 0 here. But if we start with the parabola, then the tangents here is like with slope 2.
Yeah.
That's why we consider not all the vectors, but only which fits here. That's exactly all the vectors which like that. And so you can produce such formulas for everything, just using this lemma that the area of triangle here is given by such formula. And if this formula is nice, then you have a nice formula at the end. If it's not very nice, then still you have some formula. Did I answer your question?
Well, we thank the speaker again. The next lecture will be at the Adam Auditorium at 3 o'clock. So we need